Mikolaj Fraczyk, who will talk about minimal submanifolds, higher expansion, and Cabal subdividing.
Thank you. So, yeah, thanks for the invitation, and thanks to everybody who stayed for this last lecture. I'd also like to thank the organizers, the last speaker, for putting up this wonderful week. I don't know, will we clap? Yeah, so my talk will be probably furthest from the barycenter of all the talks that happened here, because there will be some Riemannian geometry, and only at the end there will be some application to stability. So, right, I'll talk about minimal submanifolds and higher expansion. In locally symmetric spaces. This is some approximation to my title. So let me maybe start by defining for you what is a minimal submanifold, because I won't assume that everybody knows that. So we will work with a Riemannian manifold M. This is a Riemannian manifold. I don't need to assume right now that it's compact, but I'll just assume that it's complete. And right now, well, do I want boundary? No boundary so far. So, and dimension will be n. So it's an manifold. And we'll have a submanifold S. This will be a C1 submanifold of dimension k. K will be some number typically less than n. So on M, we can define k-dimensional Hausdorff measure. Yeah, probably there is either too many S's or F's. Which one? Hausdorff.
Too many S's.
Too many S's. Hausdorff measure. And to make sense of this measure, we have to first restrict it to some k-dimensional set. And when you restrict this measure to S, that's the only thing you need to know about it. This is the same as induced Riemannian volume of S. Right. And we'll say that M is minimal if you first, I'll say it in words. If you cannot lower the volume or quickly change the volume of S by deforming it locally. So formally, this will mean that S is minimal if for every deformation T goes to ST, we'll assume this is everything C1. We have that the rate of change of the k-dimensional measure of ST is 0. So maybe a few remarks are in order. So this doesn't actually, the name minimal might be unfortunate, because this really means that S is like a critical point of the area functional. So maybe the word stationary would be better, but that's what stuck. So I write S is a critical point K area functional. What are examples of such manifolds? So first, if S in M is totally geodesic, that means that every geodesic inside S is also a geodesic inside M. Then it follows that S is minimal. 2, if S minimizes area in its homotopy class, then also we say that S is minimal. This implies that S is minimal. And the last example, it's something I'll just say informally, soap bubbles. So there's the traditional examples, soap film. It's a traditional example of a minimal surface. When you see lectures about minimal surfaces, you can see the pictures of, you have some wire, and there is this film, soap film, spun by this wire, and the shape it takes, it's a minimal surface, right? So here, this is maybe a little bit different case because you have this boundary which is fixed, but locally, when you would try to move it a little bit, you would necessarily, you would infinitesimally you wouldn't change the area. Okay.
So you have this definition where it's a critical point. So could you have something that locally maximized area and though it still be like?
Yes, maximizer. Well, you cannot locally maximize the area because you can always introduce more folding, but you can allow for some directions where the area would increase in the second order. Like that's still legal. For example, this is being totally geodesic. It doesn't imply that you are area minimizing. Maybe help me out. Fourth example: when I have a sphere, those principal subspheres that pass there's restriction to the sphere to lower dimensional subspaces. They are minimal submanifolds, but you can see that there are some deformations. Like let's say you try to move it up to get something like this. You would be actually decreasing the area, but still we will call this thing minimal because this decrease in area happens only in the second order. If you do Taylor expansion of this function, you would only see it in the second order. And in the applications of minimal surfaces, especially what I'm going to talk about, many examples will actually be like this. So they will have some directions where you infinitesimally will actually increase the area, but only in the second order. I think I'm not using this face efficiently enough, but at least can you see this? Okay, so in practice, when we are working with those manifolds, we have to translate this condition into some kind of local property of S, expressed using differential geometry. So you have a lemma, and I won't use it, but I'll write it in case somebody here likes differential geometry even more than me. So S is minimal. Then this implies this is equivalent to saying that the trace of the second fundamental form vanishes. This is our first characterization. And the second, we will see, well, this is enough. But we need something which will be easier to use, and this is the first variation formula. And is a formula that basically tells us what happens with the area of a submanifold if you flow it by some flow on M. So let Y be a vector field.
When you say area, it doesn't necessarily mean that you reduce to two-dimensional objects, right?
This thing?
Because you said area. Area does not necessarily imply.
Yeah, I will use area for any volume which is less than volume of the ambient space. Yeah, it's K volume or K area, something like this. Okay, so we have a vector field of M, and we consider the flow given by this vector field. So this is the map from M cross some interval minus epsilon epsilon back to M. And this flow satisfies the property that if you look at the derivative of phi t at the point x, this is the same thing as the field y at the point phi t x. So the flow lines of this flow, they exactly follow the vector field. So it's a standard PDE theorem that those. If you assume that y is reasonable enough, maybe assume that C1, this flow will exist, and it becomes an action of R on the manifold, and we can compute how this K area of phi t of S changes over time, and this is given by integral over S of the divergence of the vector field y with respect to S dhk. And this, again, look, if you don't do Jagiellonian geometry, this might not tell you much, but I've specialized to more specific case where our vector field is given by a gradient of a function. So if f is a function of M of R is C2, then phi t is the gradient flow, then I can rewrite this first variation of the K area as follows. This is just the integral over S of the trace of Hessian of F restricted to the tangent space of S. And this is something we can actually work with, because you can choose functions f in such a way that you know exactly what the Hessian is at every point, and then you just need to take its trace restricted to the tangent space of S at this point. So I guess I should be, here I gave you a formula which is only for t equals 0, same here. Okay. Right, and because of those formulas, we know that S is minimal if and only if this integral over S of divergence of any vector field is 0. And being minimal implies that integral of traces of Hessians restricted to tangent space of S is also 0. So this is something that we can actually use to work with those manifolds. Okay, so now what else I can say? So I didn't assume really that my Riemannian manifold is compact yet. So I guess to avoid problems with convergence, let me add this condition here that Y is compactly supported. Supported And let me add that it's C1, just so everything makes sense. Okay. So this is actually the extent of what you need to know about minimal submanifolds to apply them to problems related to expansion and stability. It's really not much. So now I want to talk about wastes of manifolds and topological expansion. I think in this conference, I missed the first day, but we didn't really talk about higher expanders so much. But it's something which is close to stability problems. So suppose we have again a manifold. This time it will be compact, Riemannian manifold, and I have some function f that goes from m to Rd, and you will need to add some conditions on this function, but you shouldn't think about them too much. So this function is either smooth generic or PL generic, which just means piecewise linear generic. Those conditions are only to ensure that the fibers of this map are not too weird. So I can define waste of the manifold or of the map. First, the waste of the map, d wastes of the map F. This is by definition the maximum h n minus d Hausdorff measure of the fiber of this map. So I look at all t's in the domain, in the image, and I take a maximal n minus d dimensional measure of the fiber. Under our genericity conditions, those fibers will be essentially look like n minus d submanifolds. So this will make sense. This will be finite, and those conditions are just to ensure that you can reasonably talk about Hausdorff measures of the fibers. That's why it's not really important what you put here. And two, so I can also define waste of a manifold itself by taking the minimum overall functions from M to Rd, satisfying some genericity condition. And I look at minimum of the wastes. And so maybe just to think about concrete example, you can look at all possible maps from a sphere down to, I don't know, down to R. And we typically imagine that the preimage of a point in R would be some kind of curve. And we're asking about minimal, maximal size of such a curve for all possible ways to put a sphere into a unit interval. And it's kind of intuitive to expect that this cannot get too small, but I should move it up. Let me move it up so you see something. And in fact, it's the theorem of Algren. It's not entirely trivial. Algren. That this d waste of m is positive if d is less than n. So you cannot find maps where all fibers will be super small. This is impossible. What will be more interesting for us is the link between this problem of wastes and minimal submanifolds. But maybe before we go to that, I want to give you a definition of topological expanders due to Gromov. It will be specialized to the setting of Riemannian manifolds. So, definition: a family Mi, I in some index set, is the expander if the d wastes of all submanifolds are bigger or equal than a constant times their volumes. And this is essentially the best thing you can hope for. Typically your fibers will not be bigger than volume unless you can make your map very weird, but if your map is very regular, the maximal size of the fiber you can expect to see is roughly constant times volume. And expander families are families where this is essentially the best you can do. Gromov, well, I don't know if it was Gromov, but it's quite easy to see that if you have a family of manifolds which has a uniform spectral gap for Laplacian, then they're one expander. And Gromov asked for a higher version of this. And his question was, are there bounded geometry families of D expanders, D at least 2. So for D1 it was easy to find them. For D equal 2 you can find families which are expanders quite easily if you allow for unbounded geometry. But if your geometry is bounded, this was a hard problem. So now I'll tell you how minimal submanifolds relate to this problem. So there is a theorem, a very difficult theorem, on green pits. Which roughly says that there is, and I'll explain in a moment what it is, but you can think of the stationary varifold just as coming of a bit weirder type of minimal submanifold, S inside M of dimension n minus d, such that the d waist of M is lower bounded by the n minus d dimensional area of S. And stationary varifold, this is a generalization of a minimal submanifold. And roughly speaking, stationary varifold is like a minimal submanifold with branching. So you don't have to, this thing doesn't have to be a manifold everywhere. You can allow for some branching, some kind of weird cuts and connections. Yes?
Just to clarify, for the definition of D expanders, are you also asking that the volume of the manifold should grow to infinity? Like just for graphs that the number of vertices grows to infinity?
Right, yeah. In the question, exactly, we will want that. Thank you. So, because this minimal stationary varifold is pretty close to being actually like piecewise a manifold, all the formulas that I wrote here still make sense for them. You can still integrate Hessians, traces of Hessians, take divergence. There will be some points at which this doesn't make sense, but they will be like lower codimensional sets, so they won't affect the integrals. Everything so far still works. And this is very powerful because in some cases we can classify stationary varifolds of a manifold, and in that way we can understand its waist. So the first instance of this of like applying this theorem to the problem of waste was due to, I think, Pitts himself, where using that you can show that the waste of an n sphere is equal to the n minus dimensional volume. So I'll use vol. I don't know why I want to use vol. I could write h n minus d, but it feels weird. Of n minus d dimensional sphere, and that's because in a sphere we can classify stationary varifolds, and the only ones that appear are just subspheres. So this copy of Sn minus d is up to rotation the unique non-empty stationary n minus d submanifold. Sorry, n minus d varifold of Sn. And now we understand what is the waste of the sphere. So this gives us some hope that in order to attack Gromov's problem using Riemannian geometry, we could try to look for families of manifolds where you can say something about minimal submanifolds or stationary varifolds. You would want to say that all of them are large, of area comparable to the volume of the ambient space. So this is not how first examples of the expanders were constructed. Now I will give you the history. So progress in the expander problem. So first, maybe 0. Family of spheres Sn is the expander for d less than n, but it's not bounded of bounded geometry. Because as you increase n, the dimension changes. There is no d less than n for any fixed d. Yeah, this is not what we were looking for. Historically, this was the first example. Now, one of the breakthroughs came with the work of Kaufman, Kazdan, Lubotsky. Alex is not here. Maybe he could have some remarks about this construction or the history. They constructed bounded geometry two complexes. CW complexes, which were two expanders. And this was extended to any dimension, any d, by Evra Kaufman. Same, so bounded geometry CW complexes, which are K-expander families. For any K, why did they switch from D to K? I don't know. For any D bigger or equal than 2. So both those constructions used these buildings and resulted in something that is quite far from being a manifold. The first natural manifold examples are due to Roman and Uri. And you can take M is a spherical manifold with pi 1 of M with property T. And then the family of finite covers.
Actually, you don't need a spherical.
So any manifold, right, with this. The family of finite covers of M are 2-expander family. So this is some list of examples. All of them used, those two works used local criteria a la Garland to establish cosystolic higher expansion for those families, and cosystolic higher expansion implies topological expansion. While this work was more algebraic, working with chains, I would say, and norms on chains. And then in a joint work with Ben Low, we used this minimal submanifold approach to show that the family of octonionic hyperbolic manifolds, which are certain type of locally symmetric spaces of rank 1, is also a 2-expander family. Manifolds is 2-expander. Okay. So maybe just to refresh your memory, or you see it for the first time, define the things. To construct those octonionic hyperbolic manifolds, you need to take a semi-simple Lie group, which is F4 minus 20, which appeared at least once in the talks before. Take K, which is maximal compact subgroup. I don't remember what it exactly was. And we get the space of, we get the octonionic hyperbolic plane by taking the quotient of G by K. In this way, the isometry group of H to O is just our initial group G. And the manifolds that we're looking at are just quotients of H2O by lattices in G. So our manifold is of the form gamma, H2O mod gamma. Right, and we'll assume, because the Algren-Pitts theory is developed for compact manifolds, we'll assume that lambda is co-compact. So that we get a closed compact manifold. So the way we proved 4 is that we just gave a lower bound on the area of minimal submanifolds in appropriate range of dimensions. So with M as above, if S in M is a 14 stationary varifold, so stationary 14 vari varifold, then we can say that the 14-dimensional volume of S is at least some constant alpha times the volume of M. And this alpha is uniform over all manifolds in this family. 14 is exactly codimension 2, so dimension of M is 16. So 14 in this case is just n minus d. And now, because of Untitled theorem, this lower bound on the volumes, 14 areas of stationary varifolds, immediately implies a corresponding lower bound on the waist. So this is how we deduced it. But in fact, this theorem, it tells you something more than just waist inequalities. Because, for example, you could imagine, this is not exactly true, but you could imagine that if you start with any 14 cycle, so codimension 2 cycle inside M, you can try to deform it to minimize its 14-dimensional volume. This is something analogous to what we want to do in higher expanders. There we kind of are massaging cocycles, but in geometry we're working mostly with cycles. So we're trying to minimize the volume, the 14-dimensional volume of the cycle. And it's reasonable to expect that in the limit, you kind of deform it to something which is minimizing the volume, and you cannot deform it further. And if this is the case, then this theorem immediately tells you what's the lower bound on the initial cycle, right? Because if the initial cycle violated this bound, then you cannot possibly deform it to a non-trivial minimal object. There was a question?
Yeah. So you know that for 13 this is not true?
We don't know. We don't know.
So you don't know if there's like it's a degree-free expansion?
Codimension 3 is where our methods are on the boundary. So we probably could make it work with a lot more work.
Possibly that
It's possible we could show it for
have a free, like the dimension free weights are also bounded?
Probably. Probably you could show it. Now we don't know what's the truth, what's the natural barrier where you stop seeing that. Definitely this group contains rank 1 subgroups. So there will be some which will produce for you some total geodesic submanifolds in those spaces M. And they are kind of one of the natural barriers for this theorem. So you cannot hope to prove those theorems in the dimension where you start seeing total geodesic things, because you can make them very small compared to the ambient space. But our method, here in codimension 1 and 2, it works well. In codimension 13, certain inequality that used to be strict stops being strict, but still works as non-strict inequality. And with more work, you could probably make our argument work. Below 13, we would need substantial new ideas. Okay, but now I want to kind of pitch for you a stronger version of expansion, higher expansion that can be used, can be proved using those geometric methods. And as far as I see, I would be surprised if it could be proved using purely algebraic methods. Okay, but
What's alpha?
Alpha is some positive constant. So alpha is alpha m is positive. Depends only on the alpha depends on nothing. On hyperbolic octonionic space. Yeah.
It's a numerical constant.
It's a property of the
It's a numerical constant. So it's some number.
Yes. We don't make it explicit, it's some number, positive number. But it doesn't depend on it. Now I want to define for you homotopy D expanders. And I'll specialize to D equal 2. Maybe too early to talk about definition. And those guys, homotopy to expanders, will be very related to certain stability properties. Okay, so first I need to define some kind of weird notion of W domination. So M is again M will always be right now a compact Riemannian manifold. So I'm not requiring it right now to be a locally symmetric space. It can be anything really. I have three subsets, N1 and 2W. So N1 and 2 are subsets containing W, which is a subset of M. Those are closed subsets. And for the definition, we don't really know, we don't need more than this. Usually it will satisfy some regularity properties. They will be varifolds. And we say that N1 W dominates N2. So this is, and we write RO like this. If you can find kappa, a map, which makes the following diagram commute. So we'll see here pi1 of M without W. This can be mapped into pi1s of M without N1 and pi1 of M without N2. Let's call those maps iota 1, iota 2. And I require this map kappa to be a map from pi1 of M1 without M2, which makes this commute. Okay, and you can, the reasonable question, what happens if my manifolds that I get in this way, or spaces I get in this way, are not connected, and how do I talk about fundamental groups? I basically require this as a maps within groupoids, or I require this for every connected component. Component of M without W. Okay. So this definition might look strange. We got it with Ben only after working for a long time on this problem, and this is what kind of popped up eventually.
So the kappa is just a group theoretic map, right?
Group theoretic abstract map. We don't require anything of this map. I'll try to give you some geometric intuition. What does it mean? So you imagine you have your N1 is like some kind of a loop in a 3D space. This is N1. And N2 will be just a maybe smaller loop. Yeah, let's make it, no, this is too trivial. Let's make it a point. This is N2. And as W, I want to take some kind of a surface that feels, this is a bit color, that is filling N1 and contains N2. This is W. So the property that we look for is that any loop that can be tied around N1 but cannot be tied around N2 is cut by W. This is intuitively what we would want. Another type of intuition that we'd like to have is that if N1 W dominates N2, then any cover, any branched cover around, okay, with branching locus. Maybe I'll write a diagram for you. Because this relates to cover stability. Oh, how do I do this? Okay. Do you see this still? So the property that that we can get from this W domination is that if M1 is a branched cover of M with branching locus N1, and then there exists a cover M2 branched around N2 such that the covers M1 without the preimage, let's make it rho 1, rho 2, M1 without the preimage of W is isometric to M2 without the preimage of W. Yeah, they both cover M. So you have like a commuting diagram. So in maybe in plain words, you can any cover you can tie around N1, you can also tie around N2 after cutting along W. That's what we want. And this is a property which is very useful for cover stability. So what we prove with Ben, which is like a stronger version of this theorem on minimal submanifolds, is that I didn't define homotopy to expanders, but I'll tell you our theorem, and then it will be clear what the definition is. So if M is a closed octonionic hyperbolic manifold, S inside M is a 14 varifold with with 14-dimensional volume of S less than alpha times volume of M. So alpha is some alpha depending only on I would like to say it depends only on the octonionic space, so on nothing, but it really depends on the injectivity radius or systole of M. So if you have 14-dimensional varifold in M which is small, then you can find W which is a 15 varifold of a 15-dimensional volume controlled by a constant times the 14-dimensional volume of our S, such that SW dominates an empty set. So, because we have this theorem relating W domination to branch covers, as a corollary, we know that we learn that branched covers of octonionic hyperbolic manifolds that have small branching locus can be cheaply cut and reconnected to form a true covers. And that's the kind of cover stability phenomenon that you can prove using those methods. So corollary. Branched covers of M with small branching locus true covers. And by closeness, I mean exactly this condition that you can cut a subset which is one-dimensional higher of volume which is still small compared to the total volume, and reconnect your thing to form a true cover of your manifold.
When you say small branching locus, you mean averagely along the manifold?
Small branching locus means that, okay, if n is the branching locus, then I want 14-dimensional volume of n to be less than alpha times volume of the ambient manifold. So it's exactly like, in isophic approximations, like think of this as an error. You require error to be small compared to the total size of the space. So I think it doesn't make sense for me to try to talk about the proof of this theorem. It's if you're interested, I'm happy to tell you the details. It uses something called monotonicity estimates for minimal submanifolds. So there is a Riemannian geometry component. It uses spectral gap, and it uses some tools from geometric measure theory like Federer-Fleming deformations. So there's a healthy mix of methods.
Where does it use octoniate?
Sorry?
Where does it use the Cayley hyperbolic plane?
The Cayley, oh yeah, that's a good question. So, okay, we need to use two things. Maybe okay. I'll tell you then. Just the main ingredients. So main ingredients are so first you need to have a very good spectral gap for Laplacian on M. And this is one of the reasons why we stick to octonic hyperbolic manifolds, because they have very good spectral gap, which doesn't really depend on the manifold. It's like proof using only geometry of octonic hyperbolic space. So this is okay for H2O by constant. And this is also the same thing that Corlett used to show growth gap theorems for F4 minus 20. And the second ingredient are the monotonicity estimates. And they roughly tell you that if you have S, which is a subset of X, X is the symmetric space, and S is minimal, then for almost every S in S, you have, you know that the volume of the balls, so I should use Hausdorff measure. So I look at S, I intersect it with some ball of radius R around the point S, so BSR. This is bigger than exponent times some kappa k times R minus S, so S is a bad name, R minus T, times the volume of S intersected with a T-ball around the same point. So you kind of know that when you look at volumes of balls around points of S intersected with S, they grow exponentially fast with some specific rate. And this kappa k, it can be computed in terms of geometry of the symmetric space. And for example, I can write it for, let me put some spaces here. So for Hn, hyperbolic space, this kappa k is equal to just k minus 1. And this is Anderson. This is classical. And his result was in general about every space of sectional curvature at most -1. So you have this growth rate for volumes. But it turns out that if you, in your symmetric space, if you see curvatures which are even less than -1, you can improve this. And I'll just mention like what's relevant for us. So we showed that kappa 14, so the growth rate of volumes of 14-dimensional minimal submanifolds in a finitely hyperbolic space, is at least 18. And this is, if you know a little bit the theory of those groups, and you know growth gap theorems, this is suspicious because this volume grows in some sense faster than spectral theory would allow it to. And this is kind of a source of tension. On one hand, we have that those volumes in the balls grow super fast. This translates to certain decay rates for the heat kernel acting on S. So it says that it kind of, if you flatten this, you put some mass on S, you flatten this mass on the manifold by hitting it with heat kernel. On one hand, spectral gap for Laplacian tells you that this should dissipate very fast, unless your S occupies positive proportion of the space, in which case it kind of goes to a constant. But if it's very small, then you kind of, this decay is super fast. But on the other hand, this monotonicity estimate says that it cannot decay too fast. And you have a contradiction. So this is kind of the source of tension. This is how we prove the theorem about minimal submanifolds. When you want to prove this homotopy to expansion property, you have to work harder because your manifold cannot be assumed to be minimal. So you kind of decompose this proof, try to run this proof regardless. If it works, then you're happy. If it doesn't work, it gives you some information how to deform the manifold to lower dimension, to kind of lower the volume. And that's how it went. I wanted to, 2 minutes, I don't have any time.
So for quaternionic hyperbolic?
For quaternionic hyperbolic, our proof would give you only codimension 1. But this is not interesting because codimension 1, you already, ordinary spectral gap can give you comparable things.
Why that? Why couldn't it give only?
That's because there is this delicate interplay between the quality of Laplacian, spectral gap for Laplacian, and the quality of this monotonicity estimate that we have. And kind of, the two give you some range of dimensions where you can say something. And in octonic hyperbolic space, it's like only 2 dimensions with third on the boundary of the method. So we kind of don't do it. For quaternionic, it's just only the first codimension is on the boundary of the method, so we probably could do it, but it would be work for nothing. For higher rank symmetric spaces, this part of establishing monotonicity estimates is much harder, but once we will do it, we expect to have a range of codimensions which is linear in the rank. So yeah, so this like octonic hyperbolic case is like the test case, the first case where we can say something, but we expect those phenomena to be way more general. Yeah, and that's, I think I should finish.
Is there anything known in higher rank up to now?
So the result of Roman and Uri, they tell you that families of covers of a manifold, of a higher rank symmetric space,
That's all.
they are 2-expander. But we don't know 3-expanders yet, unless something new happened recently.
And to deduce the corollary, you just need an expansion?
This corollary, I just need this homotopy to expansion to have this corollary. Whenever,
Whenever one has it, one has a corollary.
Yes, and I'm out of time, but there is a version of this property of 2-expansion, which would allow you to say something about not branched covers, but arbitrary manifolds with boundary, which would potentially be useful for flexible stability. But this would be much harder to establish.
How does both the W dominating and also relates to the simplicial complex?
You could, so you could define this for simplicial complexes without problems, but there, like when you're proving things about this W domination, it's more convenient to work in a manifold. Because in a manifold, you know that if you have something of codimension 3, well, and this is true everywhere, but okay, because I was thinking about this problem, what happens for Buhattis buildings, etc. And it looks like there, because the dimension is so small, your objects where you could use analysis to show those things are kind of, they don't have enough room. I don't have enough room to do certain constructions because the dimension is like so low.
Is this notional varifold flexible enough so that you can realize every integral homology class by a varifold? I mean,
yes.
cycle, not
yes,
class.
yes. Yes. Definitely, yeah.
Questions? So if not, let's thank the speaker and all the speakers of this week again.